So good afternoon, everyone. My name is Martin Min. It's my pleasure to give the final deep learning lecture. So in this lecture, we will cover the unsupervised learning, especially about the deep generative models, variational autoencoder, and generative adversarial networks. So in the previous lecture, we talked about convolution. I want to emphasize one thing is about like how the convolution is done. You can, for example, you give a 5-to-5 input, right? This cartoon picture shows that how the 3x3 convolution kernel is actually computed. And then finally, for example, if your input has a RGB channel, right? And then each kernel, they must also has the RGB channel. But for each kernel, they only output one scalar value. What does it mean? After you do the convolution, that's an element-wise multiplication, and then you need to sum it. You need to sum all these kind of like computations involving these three, three channels. So let's think about like a one-by-one convolution. So, one by one convolution kernel is just like this is three by three convolution, right? Because the RGB has the RGB input channel, the actual filter is 3 times 3 times 3. But if it is one by one convolution, you see it is very popular in like image segmentation or in a fully convolutional neural network or even in ResNet. You may wonder, what does one by one convolution do? Because one by one convolution is just like a multiply each element of the image by a scalar, right? And then you probably the first idea coming into your mind is that, well, you multiply your image by a scalar, it doesn't do anything. But actually it does something. Why? You look at it, because your output plane is that you need to sum the output of all these kind of channels, right? All these RGB channels. If you do the one by one convolution, it is like that. You multiply this RGB, map this RGB three values into one value. That's kind of like a fully connect layer. You multiply by a 3 times a 3 by 1 vector, right? You can think about it. I have a fully connect layer connecting each column here into a value in the output plane. So why the one by one convolution is so useful? Because here it is RGB 3 channels, but in the middle of your convolutional neural network, you might have 512 like kernels, right? It means that for each position in your input image, you will have 512 values. When you use a one by one convolution, it kind of serves as a fully connect layer. You convert this 512 values at this image position into one scalar value, right? So then, and then you can control how many one by one convolutional kernels you want to output. For example, your input is like a 512 kernels, and your image size is like say it is 100 times 100. And then if you choose like a 10 output one by one convolutional kernels, then you can convert this kind of like you compress this kind of 512 values at each position into 10 values. It's a fully connect layer. Then your output matrix will be 10 times 100 and times 100. 100 times 100 is the size of your original input image plane. So this is what I want to say. And then about that, you need to understand one by one convolution. It does something like a fully connect layer. It can reduce your parameter by embedding a lot of kernel planes into a smaller number of kernel planes, or you can just resize. You can even convert 20 output planes in the middle layer to say 1,000 output planes in the output layer, or something like that. So this is why the one by one convolution is useful in the fully convolutional neural networks for image segmentation, for ResNet, for a lot of other applications.
I have a question on that.
Okay, any question about this? Thank you.
I don't understand why the output is 3 by 3 by 2. I guess what I'm picking up on is
you think about it, right? Because you see, I think I give you equation in the last lecture. It is you move this see I think now we have the padding, right? On both sides we pad the 0. It's up to you. You don't need to do padding. Sometimes people use padding, right? For biomedical applications, for image segmentation, or for other things, it's up to you to decide whether you want to use padding, right? For sequence classification, you probably don't want to use padding at all. Okay, see, I have the paddings on both sides, right? And then my kernel is a 3x3. Say the first output is convolved with this 3x3, right? Now my stride is 1. Next time you have the convolution of this 3x3. You get it? The third one you get it is I think this is I think they use a stride of 2 here. Let's see. Oh yes, this is a stride of 2. I just like you know I just get you know I get a like I get a what did I say? I just get a screenshot of that animation. So I think here it is a stride of 2. So the first one is I think it's here. Okay, if you use stride of 2, the third one is here. The second one is here, and the third one will be here. You skip one. You got what you got what I mean?
Yeah.
It's stride of 2, but if it is stride of 1, it's not 3x3. You probably you need to use that equation 7. We can count it like this is 1, 2. Basically 7 minus 3 divided by 1 is 4 is 5. You will get 5 by 5. You get it? So I will show it to you.
Yeah.
1, second, third, fourth, fifth, right? This is stride by 1. But why we choose stride? The stride is that you can reduce a bigger size of input into a smaller size of output. You use stride. For example, I use stride of 4 means that I will skip 3 of them. The first convolution is here. I was stride of 4 means I will skip 1, 2, 3, and I will start from here. You see, you only have 2 outputs. You got it. You have a 2 by 2 like outputs if you stride of 4.
Yeah, that makes sense.
Okay, you got it, right?
But the third value, 3 by 3 by 2.
Because I have 2 kernels. You know, your output, you know, this is your 3 by 3 is your output, is the size of your output image. 2 is your kernel. Okay. So say I use 100, this is the first kernel, has 3 planes because you need to cover the RGB channel, right? And then sum it. And then this is the second kernel. Say if I have 100 kernels, your output volume will be 3 times 3 times 100. Because for each one, you get a 3 by 3, like for each kernel, you get a 3 by 3 output, right? So then your index will be 0 to 1 and then to 99. You get it?
Yeah, yeah. Thank you.
Okay, so then let's, any other questions about how the convolution or 1 by 1 convolution, why 1 by 1 convolution is, you know, seems to be naive, but actually very important. That's a very important trick because, you know, if you don't think about it, most people, they don't understand that 1 by 1 convolution is so important because it is used widely in the image segmentation and in ResNet and in a lot of like commonly used architectures. Okay, now this lecture, let's talk about the unsupervised learning. And so this is I'm not sure if you heard of like the graphical models. Basically, it's unsupervised learning, and then you want to maximize. You give me some kind of data, X, and then I just want to learn a model that generates this data. It means that I want to maximize the log likelihood of my data point X, Px. So this, I need to maximize this log likelihood, and then I need to learn this model. So for fully observable model, this model is, for example, for Markov random field, right? And then basically your model is like everything is every variable is observable. But for the a lot of probabilistic models, like say like Boltzmann machines, right? And then or like even mixture of Gaussians, right? and then you have hidden variables. So in mixture of Gaussian, your hidden variable is the assignment of each data point. So it means that you don't know what is the cluster assignment of each data point, because you say you have 10 Gaussians, right? And then you maximize the log likelihood of your data set, but actually you have a hidden variable of h denoting the latent assignment of each data point to each to the clusters. So you don't know that. That's for here I show a deep neural network kind of like a graphical model with the many hidden units. Only this is your observable X. Say this is an image. This is, you can observe this image, but I want to train a deep generative model to maximize the log likelihood of this observing image. I have a lot of like hidden units. I don't know the values of these hidden units. So in the generative model, you sample some kind of like a prior distribution of these kind of hidden units, and then you sample their values, and then you can generate your some data. But the problem is that when you train this model, learn the parameters, the connections between the hidden units to hidden units and the hidden units to the observable units, all these edges denotes the parameters of your model. And then you need to do inference. What does inference mean? And then given your observable input image, you want to know the values of these kind of hidden units, just like in mixture Gaussian. Given the current data point, I want to know which cluster this data point is assigned to. And then I can learn the parameters. The parameter in mixture Gaussian is just like a mixing coefficient, and also the mean and the standard deviation of each Gaussian, right? And then so here in this kind of complicated like a deep generative model with hidden variable, it's the same thing. You want to infer these kind of values of this hidden unit. It's called inference. So, but for a complicated like deep generative model involving so complicated interactions of the hidden units, EM algorithm doesn't work well, because you don't have a closed form solution for as done in a mixture of Gaussian, right? And so what people do is that they use a variational inference. So variational inference is a trick like you still want to maximize the log likelihood of your input data, but instead of directly calculating the posterior distribution of all these kind of hidden variables values given the input, I want to say I just define a tractable, a simple like a distribution, say factorize the Gaussian distribution for each node here. Say this is a Gaussian distribution, this is another Gaussian distribution. I use 10 Gaussian distribution to represent this hidden representation. I denote my like a variational hidden representation as Q, inference network as Q. So to represent the variational posterior. And then you still want to maximize the log likelihood of your data. And then fortunately, we can use a bond to convert this kind of like this kind of maximum likelihood of estimation of maximum likelihood expression of your input data as a lower bound into a lower bound. It's called the evidence lower bound. So actually, it is like the derivation is quite trivial. You can see that your original objective is that you sum over all these kind of hidden representations Z, right? And then you can see if I write the QZ inside this kind of log term, and then a log QZ and QZ cancels, and then I put the sum here. It is the same thing as the original log likelihood of your input. But because this log function is a concave function, using the Jensen's inequality, that kind of like the log sum is greater or equal to the sum of logs. So then I can write it down. I can convert the original log likelihood like expression into this lower bound, right? This is called the elbow. Elbow just means that just use the Jensen's inequality of concave shape of the log function, and then to convert the original log likelihood maximization into this lower bound. Okay, so in traditionally in variational inference, for each data point x, I want to have I want to estimate factorize that if we use the mean field of variational inference, I want to infer like a Gaussian, a separate Gaussian, factorized Gaussian for each data point. So then I need to, and then I maximize this term, this lower bound, and then to calculate the z for each data point. And then I use because why a natural question is that why do you need the inference? Because after you get the inferred value of this kind of approximately inferred value of this of this kind of like of these hidden units, then the sufficient statistics of this connection, right, on your whole data set. Then you can just using the sufficient statistics to update this kind of connection weights. So that's why you need this. You need to do the inference, just like in EM algorithm for the mixture of Gaussian. Because after that each data point is assigned to each cluster, the true membership, the inferred membership of your data point given a current Gaussian estimated. And then you can just calculate the mixing coefficient, right? For each update the mixing coefficient based on the current like a latent assignment of the data point. Here it's the same thing. For this complex model, it's the same thing. You need to, and then you just like for each data point, after you infer this kind of latent value assignments, you can update your network, you update your model, and then you just like given an updated model, you infer again, and then you update your model again. It's kind of like the EM algorithm, but it's not the EM algorithm. But the problem is that in a traditional variational inference, for each data point, just like in mixer Gaussian, for each data point, you need to estimate, this kind of like this kind of latent variable values. For the mixture of Gaussian, it's easy because you only have one latent variable. But for a complicated model, you have so many different latent variable. If I have 1 billion data points, I need to estimate the latent representations for 1 billion data points. That is not scalable. So that's why it's not good. So that's why the variational inference approach is not scalable to the big data set we encounter in deep learning. So how can we solve this problem? And then we can use amortized variational inference. What does it mean? It means that instead of to infer the hidden representations for each data point, how about just like I parameterize this kind of inference network using a neural network. So every data point, all the data points will share a variational inference network Q parameterized by a neural network. So it means that for I instead of infer the Q Z, the Z for every X, I just say all the data points have this kind of, their inference network will be Q, phi, H, and X. So all the data points only need to update the parameters of this, inference network, and they share this inference network. And then this is much, much better. And then it's scalable, right? Because now, the number of parameters will not grow as the number of the data points. So this is, the lower bound is the same as the lower bound we used in the traditional variational inference. The only difference is that we just use like a neural network to parameterize this kind of inference network and make sure that all these kind of data points share this inference network. And then we maximize this like a lower bound, the elbow of the original log likelihood term of your data points. So then you just use the mini batch gradient, stochastic gradient descent to update the parameters of your inference network and updates the parameters of your original model of this model, and then you do the maximum likelihood estimation. So any questions so far? So this is, I know this is, you probably don't know a lot of things about graphical model, but I just like using an analogy to the mixture of Gaussian, and then so that you can understand. Any questions so far? Okay, I hope you understand. And then let's move to the reparameterization trick. So here, you just like you parameterize the inference network as a neural network, but we can actually have a more efficient like implementation of this neural network. So you can see we just instead of like using this kind of complex neural network to define a complex distribution h given x, actually we have a reparameterization trick to parameterize this q phi z given x. So what can we do? We can convert a Gaussian distribution, a simple standard Gaussian distribution, to define this kind of like a variational inference network. How we do it? So you see, any kind of Gaussian distribution has the sufficient statistic defined by their mean and the standard deviation, right? And we know that any Gaussian can be converted into the standard Gaussian using this transformation. Say if the z equals mu plus sigma times multiple element-wise times a standard Gaussian, then this kind of z will follow a complex Gaussian distribution with the mean of mu and the sigma. And we use a deep neural network to learn this high-dimensional mu and a high-dimensional sigma. Then we have some kind of nice property. The reason is that this neural network, the neural network parameterizing this mu and sigma are all deterministic, right? We can use backpropagation to backpropagate. And only the stochasticity is only happens in this simple like a standard Gaussian, right? Then we decouple this kind of stochasticity and the deterministic of the deep neural network. You see, we can use this kind of simple reparameterization trick to transform a simple standard Gaussian distribution into a complex distribution inference network, the z given x. But the nice thing is that we don't need to perform sampling. And then we only sample, from the standard Gaussian distribution. We can use backpropagation to backpropagate the error signal from our objective function to the z, to the phi, to the x, because all these kind of nodes are deterministic, just using this kind of trick. So this is nice. This is why, the reparameterization trick based on the amortized variational inference is so popular. There are two breakthroughs here. One breakthrough is amortized variational inference. Instead of like, you have you need to infer the latent value factorized like variational like a parameter for each data point. Now you make sure all the data points share like a inference network. And then we just further like facilitate our computation by decouple, by transforming this kind of complex Gaussian distribution into a simple Gaussian distribution, so that the complex Gaussian distribution only involves deterministic calculations, and then only the stochastic it only happens in this kind of simple Gaussian distribution. Now we can use we can use a backpropagation to update our inference network and our model P. This is our model, and then this is our inference network. So any questions so far? And then I hope you understand the reparameterization trick. So of course, this is only one form of like a reparameterization. You can think about whether there are some other kind of distribution. You can reparameterize their sufficient statistics. You reparameterize their sufficient statistics into using complex neural networks, and then you can convert that kind of like a complex distribution into like reduce that complex distribution into a simpler, like a standard distribution that doesn't have any parameter at all. You see, this standard Gaussian distribution doesn't have any parameter, and all the parameters can be learned by by the backpropagation. So this is a nice thing about like a variational amortized variational inference and reparameterization trick. Okay, let's go to our like objective function. We want to maximize the log likelihood of our data point, right? So we see finally it will be the lower bound will reduce to like if you rewrite this lower bound the elbow form we just talked about here, and then we rewrite it in another term, it becomes a KO divergence. It's some exercise. You can do it by yourself. Just look at the slides. And then this lower bound elbow becomes a KO divergence between your posterior distribution and your prior distribution. Prior distribution is just a Gaussian distribution, standard Gaussian distribution. And and then you see this term. I sample the Z from my posterior distribution, and then I want to maximize my, the log likelihood of my X given Z. So what is this? This is just reconstruction. You want to reconstruct the X and then given Z. Let's see why is that. If we assume that our like a PXZ is some kind of like follows the Gaussian distribution with a mean of Fx and some kind of standard deviation of a diagonal standard deviation of CI, and then it will becomes like if you maximize the log likelihood given a Z, it's the same as minimizing this reconstruction error. See, okay, then we can further reduce our, then we can write it down, our objective function. It will be equivalent to, we just like, we want to minimize the KO, we want to minimize the KO divergence between our posterior distribution parameterized by a deep neural network and reconstruct the original input X given Z. What is that? Let's write down all this into a neural network architecture. It's like this. Given X, this is our inference network, and then this inference network will parameterize the mean and the standard deviation, and then we sample from this kind of like a posterior distribution, get the Z, and then we just like reconstruct the original output, original input. This is just an autoencoder, right? You're given the X, I have an encoder here, encoded into some kind of latent representation. The latent representation is actually, actually parameterized by a mean and a standard deviation. It's an encoder with two heads. One head outputs the mu, one head outputs the sigma, and then sample from it. And then we just reconstruct the decodes the Z into X prime to reconstruct X, minimize the reconstruction error. So this is just autoencoder. Okay. So this is a variational autoencoder. You see, the variational autoencoder is the same architecture as the deterministic autoencoder, except that we want to minimize the KO divergence between this kind of parameterized posterior distribution and the original prior distribution. The prior distribution actually Gaussian distribution, the Gaussian standard Gaussian multivariate Gaussian distribution with the diagonal covariance. So any questions so far about the variational autoencoder? So we just want to make sure you understand like, how the variational autoencoder here is actually transformed into a standard autoencoder. Like this is a encoder, this is a decoder, and then just like a plus a regularization term, the KO divergence regularization, and then everything else is the same. Because when you do the calculation, you can either sample or you don't sample at all. And then you just like using the because when you use the reparameterization trick, you just like naturally sample from it. Any questions so far? So this is a variational autoencoder. So this is the loss function of the variational autoencoder. It's the same thing. You just as the autoencoder, you just inputs the X into some encodes the X into some latent representation. You decode, reconstruct it. So your objective function contains two things. One is the reconstruction loss mean squared error, and the other is the KO divergence. You want to make sure that your Gaussian parameterized by GX and HX. GX is just a mean, and HX is a covariant, like a diagonal covariance, and then you minimize the KO divergence between this, and then the prior distribution Z is a standard multivariate normal distribution. Because this is a Gaussian, and the KO divergence between the Gaussians can be computed in a closed form. So then that's why it's easy to optimize. So this is a mini batch version of how you train it. So basically, you just you initialize your model parameter. You're given some data, right? and then you just like split your data into mini batches. And then first you initialize your model parameters. This is a deep generative model, it's a decoder. And then you like initialize the parameters of your encoder. This is a inference model, the QZ given like X. This is your encoder, and then initialize your parameters. And then you randomly sample some mini batches, a mini batch of M data points. And then you randomly sample some Gaussian, and then you calculate the gradients of your loss function here with respect to this batch of data, because we know that this KO divergence can be computed in a closed form solution, and this is a reconstruction error, just a standard like a backpropagation. So that's why you can use a gradient descent to update it, and then until convergence of the theta and phi. That's it. So this is a variational autoencoder based on the amortized variational inference. So here I give you some examples of the generated images. You can see this is in the first epoch. I just trained this variational autoencoder on the minis dataset. In the first epoch, it's quite blurry, and in the 9th epoch means that I swept all the dataset 9 times. It gets this much better, and after it converged, and then you can see your variational autoencoder can generate quite nice handwritten digits that are similar to your original minis images. Of course, there are some kind of things we don't understand here. It's 0 or 6. So another interesting property is that if you just I just embed the original version the Z, right, into 2-dimensional space. I say my encoding space Z is actually 2-dimensional space here. The mu is 2-dimensional. And then if I arrange all the data points in a 2-dimensional space, you can see, they form some kind of nice topology, right? And then from the 6, 0, change it to 8, and then change it to 1. And then this means that the variational autoencoder really learns something that is semantically meaningful. For the faces, it's the same thing. They can learn some kind of semantically meaningful representation about the faces. So you can, this picture shows that you can probably use the variational autoencoder to learn some kind of to embed your data into 2-dimensional space to see whether they can discover some kind of a semantically meaningful topology. So of course, this is the framework of your variational autoencoder, and then actually for both the encoder and decoder, you can use convolution and transposed convolution. And then I didn't talk about transposed convolution, but actually it's the same thing. And then in the PyTorch, you just call that kind of transposed convolution. What does it mean? I will not talk about it in details. You can think about it's the inverse of the inverse operation of the convolution. For convolution, right? And then you just you can convert an image into some kind of feature representation. But how about I want to convert the feature representation into the image? You can still use the convolution to do it. It's the same thing, but you need to do it in a different way. Okay. So let's compare the autoencoder to the variational autoencoder. This is a deterministic autoencoder, and then you just you given some input, you just encode it into a low-dimensional space, and then you decode it. And then your loss function is just a reconstruction error without the KO divergence regularization term. So this is the only difference between your deterministic autoencoder and the variational autoencoder. So a natural question is that what is the benefit of using the variational autoencoder? You can see that when you use a variational autoencoder, you regularize your latent space. So then, if you use a deterministic autoencoder, you only care about, you only for this input data point, you can get a perfect reconstruction. But for, say you embed these kind of data points in a 1-dimensional space, when you try to generalize out, outside the data points, you actually embed it. For example, you want to decode the points in the middle of these two data points, right? two data point embeddings, you are not guaranteed that this embedding point will be decoded into something that is meaningful. It might decode into something that is completely random because you don't have any regularization on this kind of latent space. The nice thing about the variational autoencoder is that you make sure that the semantically some kind of similar latent codes will decode it into something that is similar to each other, right? So that's why you will not have points are close to the latent point in the latent code space will be similar in the decoded pixel space. So that's a nice property to have, right? But for deterministic autoencoder, because you didn't regularize the latent space, you are not sure. You are not sure this phenomena will occur. So this is the illustration of your latent embedding. If you use a deterministic autoencoder, because you just for each data point very close to it, it might decode into something similar to your data point. But for the data points in the middle, you are completely not sure. But for variational autoencoder, because you enforce all these kind of like a posterior distribution to follow a Gaussian distribution, actually you kind of cover. And also during the training, you use sampling, right? You use sampling, you sampling from that prior distribution, and then using a reparameterization trick, you kind of cover something here. And then that's why when you decode it, this thing will be decoded into some like outputs that are similar to your inputs. Kind of makes sense, right? Any questions so far? So this is why the variational autoencoder has this nice property. Of course, there are, the variational autoencoder will have some kind of problems. The reason is that you see for many different data points, their posterior distribution overlap, right? So for example, for this kind of, if I sample a data point from this region, well, I will be not confident I should decode it into a triangle or a square because all these kind of like the posterior distribution overlap here. So that's a problem of variational autoencoder. So how can we, for a lot of applications, we need to design a conditional variational autoencoder. It means that we need to put not just like a reconstruct your X, you have some kind of conditioning. For example, you want to model, maximize the log likelihood of your output Y given some condition X. So then there are the architecture is almost the same as the traditional variational autoencoder. The only difference is that when you sample the posterior distribution, and then you need to put the condition there, and then when you decode it, you also put the in your decoder, you also put the condition in there. So, and then all the other are the same. So here I give you some like, I give you some example of the conditioning. For example, your like posterior distribution will be calculated this way. You put not just only depend on your input, but also depend on your conditioning. And then here it's the same thing. Not just depend on your decoder, not just decode from Z to reconstruct your original input, but you also put the conditioning variable there, X. Okay, so that's the one example of how to design a conditional variational autoencoder. There are many ways of doing it. Here I just show you one example, and you put the conditioning in this architecture. So you can imagine there are many ways of doing it. So I will not talk about it in details. So let's any questions so far about the variational autoencoder? To summarize, it's just the same to the deterministic autoencoder, and then you just like have a KO divergence regularization so that you will have some nice properties, and then for regularizing your like your latent space. But of course, there are some kind of like problems because they overlap, the kind of posterior distribution overlaps, and you have many choices of of designing a conditional version autoencoder. Just put your condition there. Put it in the condition in the encoder and the decoder. That's it. Okay, so if no questions, I will go to talk about the generative adversarial networks. So let's focus on the reprime transition trick again. So the reprime transition trick actually does is that it converts a Gaussian distribution into a complex distribution of X given Z, right? And then you start from a simple Gaussian distribution, and then you can if you write it down, if the Z is sampled from Gaussian distribution, you can see that your probability of X given Z is some kind of complex, like a deep neural network parameterized Z, and some kind of like this is your decoder function, and then this is your variance, right? And then your output, this is the distribution of your input image, and then all the parameters is encapsulated in this deep neural network F. So you see, you start from a Z and into a high dimensional, a simple like Gaussian distribution into a very complex high dimensional image distribution. And then all these kind of parameters are in F here. So how about we just elaborate, expand this idea, extend this idea further. And then, so a direct approach is that we can just using this trick to convert a simple function into a complex function. And then I just want to make sure, my complex function will be the same as some kind of ground truth function. So what can we do? So you can do the distribution matching. So there are several ways of do distribution matching. One straightforward way is called moment matching. We're minimizing the maximum mean discrepancy between the high dimensional feature space induced by a kernel using the kernel MMD. So basically, I transform my simple function into a complex high dimensional image distribution, right? And then I just want to using the kernel MMD and then to get samples from this distribution and then get samples from my real data. How to get samples from a real data set? Easy, just sample some data points, right? I compare their mean, the kernel mean, the mean, their mean in the kernel space using the kernel maximum mean discrepancy, and then to do it. This is one way of doing it. We can also have another way of doing it. So the idea we talk about is that we just transform a simple Gaussian distribution using a generative network into a complex distribution, and then we reshape this reshape this kind of output. We will get some kind of images. And then one way we talk about it is that we directly use the distribution matching based on the MMD, maximum mean discrepancy, or kernel mean, kernel MMD, kernel maximum mean discrepancy. But there is another way of doing it. The idea is that we train a deep neural network to do it. So, we don't need to directly use the kernel maximum mean. And then how about we just we train if we have if we have a discriminator, right? Suppose that we have an Oracle discriminator can discriminate the generated data and the real data sampled from your data set, and then you can just update your generative network to satisfy the criteria specified by this Oracle discriminator. That would be great, right? Then you don't need to use the kernel MMD. But the problem is that in practice, we don't have this kind of Oracle discriminator. Fortunately, we can treat this Oracle discriminator as a deep neural network, and then we learn from data. And this is the idea of generative adversarial network. So the goal of the discriminator is to discriminate whether a sample comes from the real data distribution, the training data, or the generated data distribution. That's easy. How to train is kind of this discriminator from scratch. Easy. We just sample some data from your training set, from the training data, and then sample some data from the generated data distribution. And then we just like a train a discriminator update. We assign the label of the training data, real training data to be 1, and then generative data to be 0. And then we can train a discriminator, right? So then the goal of the generator is to transform a simple distribution, for example, Gaussian distribution, uniform distribution, to a real data distribution, so that the generative sample cannot be distinguished by the discriminator. I want to fool this discriminator. So this is a min-max game, right? It's a cat and mouse game. And then you want to train, you sample some data from a real data distribution and some data from your general data distribution, and then you train this kind of discriminator to make sure that I really do a good job, and then to detect the fake from the real data. But then your generator try to fool this discriminator to say, I will try my best to make sure the discriminator will not distinguish my fake data. Then my fake data will be infinitely approaching to this kind of to this real data. Finally, the discriminator cannot distinguish who is real and who is fake. It means that your general data will be infinitely approach to the real data, right? No one can distinguish. So that is so in the global optimal, the discriminator will output half everywhere, because finally your generative data distribution is equal to the real data distribution. So this is the idea of the generative adversarial network published on NIPS in 2014. So this is the idea. This is a cartoon illustration of the idea. So your generative model will generate some data that and then this is you sample some real. This is your real data. Your discriminator of the network will minimize the classification error so that it will set a boundary to distinguish this real data from the generated data. But then you update the generative network to make sure that they cannot distinguish. Finally, it will be merged together, right? So this is then finally this kind of general data will exactly match the real data, and then this kind of like discriminator will output half everywhere because there is no clear decision boundary anymore. So they can prove that this is a technical detail to prove that why the discriminator will output 1.5 everywhere. So you can check the slides after the lecture. I will skip it. So this is the training algorithm of a generative adversarial network. You still use the mini-batch-based stochastic gradient descent, just as before. For training the variation autoencoder, you split your data into many mini batches, and then for each mini batch, and then for case steps, you want to update your discriminator, and then perform the stochastic gradient ascent to make sure that you will classify the real data as 1 and then fake data as 0. And then you perform one-step updates of your generative network, and then to make sure that you will fool this kind of like a discriminator by stochastic gradient descent, one ascent, one descent. Okay, then you update case steps of your discriminator and update one step of your generator. Why is that? Because you really want to make sure that your discriminator does something meaningful, right? If your discriminator, you really want your discriminator to do something meaningful. If your discriminator is garbage and then it doesn't contain any informative signal, you fool your discriminator, doesn't make sense, right? That's why you always need to update more steps of your discriminator than your generator. So this is you just iterate this process until convergence. So this is a training algorithm of your generative adversarial network based on the stochastic gradient descent. So this is the convolutional version of the generative adversarial network. So you start from 100 like a dimensional Gaussian standard Gaussian distribution, and then you use the you project and reshape it, and then into this, and then you use the convolution, and then to use the convolution layer. Finally, you make like a 64 by 64 times 3 output volume. So just a convolution, and then volume. And then now we have much better architecture, but this is the original like a classic structure of the generative adversarial network that works well for generating high resolution images. So here are generated samples of this deep convolutional generative DC GAN, deep convolutional generative adversarial network. You can see they can generate some kind of like a bedroom scenes quite well. There are some kind of artifacts here, but most of the time, you can see the images are reasonable, right? And then you just train this kind of the generator and the discriminator, and then using the convolution layers. And of course, you use nonlinear like a ReLU activations, and then until you have this kind of thing. So this is quite amazing. So, and then you can also do the interpolation results of the DC GAN. So this you start from you randomly pick two vectors, and then one vector, the first vector generates the scene here, and then the second vector generates a scene like this. And then how about I interpolate, between this? I use the linear interpolating these two Z vectors. You can see they just slowly transforming this bedroom scene to this bedroom scene. It's quite semantically meaningful, right? And then for here, and then I without window and to a window, and then you can see I just like the first vector generate a bedroom scene like this, and then second generate this one, and then I just linearly interpolate these two vectors, and then just from Z1 to Z2, you can see this slightly changes to this kind of like a bedroom with more windows. So it's cool. You can also do some kind of latent vector manipulation results on the DC GAN. For example, these vectors generating the smiling face, and these vectors generating the neutral face, and then and this vectors generates the neutral man. Actually, you can use the vectors generating the smiling woman minus the neutral woman, the latent vectors minus the average of the vectors generating the neutral woman plus the average of the vectors generating the neutral man to get the smiling man generation. You see, because I have like this is randomly 3, like I just use the mean, and then I take the mean here, and then I just do the manipulation. I can get the smiling man. Okay, this is the vector manipulation about it. So people can also use this kind of architecture, train this kind of like a deep convolutional neural network using instead of on the 2D convolution, they use a 3D convolution, and then everything else is the same. Just to train the DC, extend the DC GAN using a 3D convolution, they can generate videos. So it's a video generation, and then published in Europe's 2016. You can even generate, using the GAN to generate some music. I will show you some. I will not show the examples. You can check it like you can after the lecture. You can see that you can hear that they can generate some quite amazing like music. So another natural question is how can we extend the conditional generative adversarial network into a conditional version as the conditional VAE? So the idea is that similar to extending VAE to conditional VAE, you just like you just put the condition in the generator and the discriminator. That's it. Okay, and then just and then you just transform a GAN, a standard GAN, into a conditional GAN. So the GAN idea, the adversarial training idea, is actually very powerful. It can be used in many applications. For example, domain adaptation. What does domain adaptation do? So for a lot of, for example, for a lot of applications, we have a lot of data points in one domain, but we don't have many data points in the short term. For example, in this example, right? We have a lot of examples in this kind of like a source domain like this. But we want to classify this kind of images. We don't have many data. And then what we can do is that we want to transform the features the network learned on the source domain to this target domain without much, without much extra effort. And then what can we do? So then the adversarial idea can be used as this. So for example, you can have two neural networks. One is the source encoder, and then the other is the target encoder. and then you can make sure that you use the adversarial training idea, and then you encode the source domain and then into some kind of source domain input images into some latent space, and you can encode the target images into some latent space, and then you train a discriminator. You make sure that discriminator cannot distinguish, and then the discriminator will discriminate the features from the source domain and from the target domain. And then finally, you can update this kind of like the encoding network such that the discriminator cannot distinguish, the features are actually from the target domain or from the source domain. Then your network successfully, learn something that is common between the source domain and the target domain. So any question about the adversarial training? This idea, I think this kind of idea can be useful in a lot of biomedical applications, because you often have a lot of data in one domain, have one kind of application, but for the other ones, a related application, there, you don't have much data there, but you can use this kind of like use the adversarial training to make sure you train a common network or target or a separate network, whatever, and then you make sure that they can for a separate network with tight weights or whatever, and then you make sure that they will learn some kind of common feature representation cannot be distinguished from two domains, and then you can use your target domain, right? You can easily like apply your target like a convolutional neural network to classify your target like image, right? Even if you don't have much data like in the target domain.
I have a question.
Yep.
So in the adversarial adaptation, you're just inputting your images without labels?
You do have labels. For the source domain, you have a lot of label, right? I'm talking about is that, say, for domain adaptation, right? For source domain, you have a lot of label data, but for the target domain, you're doing the same thing just as here. I still want to do the image classification, but they have the data distribution is kind of like there's a shift there, right? But I don't have a lot of label data here. So, or you have no data, right? You have no label data on the target domain. You only have like you only have the you only have the input data, but you can still use the adversarial idea, because the adversarial idea doesn't care about the labels, right? You can say I have a source neural network, I put a classifier to classify the source images, but your discriminator only look at the feature representations of your source domain, target domain. That's why you don't need to have a lot of label data on the target domain. Does it make sense?
Yeah, kind of. Okay, thank you.
No problem. Yeah. Okay, you can also have the idea of called the cyclogram. What does it mean? And then you have two domains. One is X domain and then Y domain. And then you can transform the images from the X domain to the Y domain, and then you transform the Y domain to the X domain. You generate, okay, given the images from the X, and then you train a generator, transform it into a Y domain, right? And then given the images from the Y domain, I transform it to the X domain. And then also the cycle consistency, make sure that you have two discriminators, and then you make sure that your transform the image cannot discriminator. I have two discriminators. One is on the X domain, the other is on the Y domain. And then on the X domain, to make sure that your generated images transformed from Y cannot be distinguished from my real images from the X domain. And my discriminator training in the Y domain make sure that the transformed images from the X domain cannot be distinguished from the real images in the Y domain. And also, I have a reconstruction loss. And then given the X, I transform it to Y, right? And then I transform it back. And then I want to make sure, this kind of thing will reconstruct the original X. Does that make sense? Okay. So you see, I X and then give it to Y, and then I come back. I want to make sure I can reconstruct my original X. So basically, you have two discriminators the two generators and one reconstruction loss. This idea very simple, right? A generator, generator is a conditional generator from X to Y, another conditional GAN generator from Y to X, it's a GAN network, and the reconstruction loss. Make sure that your G you generated from the Y, GFY equals to Y, or like a FGX equals to X. It means that from X, I transform it to Y, and then I transform back. I must reconstruct the original X. From Y, does the same thing. I transform it to X, and then I use G transform back. I must reconstruct the original Y to reconstruction loss. Okay, you see, this is a nice example. I have, I can just using this kind of cycle GAN, I can transform the, the monad to this photo, right? I can transform the zebra to horse. I just, using I can either transform the horse to this zebra, and then I can transform an image using F. I can change this image from spring to summer to winter, and then if I use the G, I can change this like a winter to summer. This is cool, right? Just the idea is that you just train like a two GANs and then use the two reconstruction loss, and then make sure that this cycle consistency is preserved, because you transform to Y and then you transform back, then that must be the same X. The Y is the same thing. Y transform to X and then transform back must be to the same Y. And then train two GANs, and then also impose this kind of like a cycle consistency reconstruction loss. You can get cool applications like this. Okay. Okay, then also this is my work, and then my idea is that I just want to you give me an input image. I want to generate a video that is semantically consistent with image. What we should do? So basically, I just concatenate the conditional variation autoencoder and the conditional GAN. So that's it. So how I did it, like in details. So basically, you give me some kind of sentence, right? Say a guy is swimming in the pool, and then I will encode in some latent representation, and then I first generate some kind of rough image describing a swimming pool scene, and then given the scene, swimming pool scene, and this kind of like a guy swimming in the pool, and then I just train this kind of conditional GAN, I generate some video. So this is the architecture I do. This is the conditional VAE for generating the gist, rough image describing the scene like this, and then given the text and the rough scene of the video, and then I generate the final video frames. So, and then this is just a concatenation of conditional VAE and the conditional GAN. Here are some examples. If you give the text input, play golf on grass, you will get something like this. Play golf on snow, it will get the video like this. Play golf on water, you will generate video like this. It's kind of blurry, but this was done in 2017. So at that time, our DC GAN architecture is not that good. So here are some kind of examples of video, like playing golf on grass field. You can see. You can even say playing golf on snow. It will get a scene like this. Playing golf in water, and then it will give you a video like this. More examples, say like sailing on snow. This is cool, right? And then it can have kind of like understand the snow should be in the background, and then they can like a scale here, and then they can sail here. And then for running on sand, the data set never contains any kind of video like a running on sand or running on the sea. We kind of there are more examples here. So in 2019, 2018 actually, we improved that architecture a little bit, and then we can generate some videos that is better quality. For example, like say playing golf on grass, it's much better than much higher resolution than the previous one. For example, like people swimming in pool, it's better quality. But now, today I can generate much better quality than this. Much better quality of videos than this. Our paper will publish, I think, hopefully this summer. So actually, there is a media reports from Science and MIT Technology Review and Communications of ACM about this kind of simple like algorithm, concatenating the conditional VAE and the conditional GAN. It says new algorithm can create movies from just a few snippets of text. So that's it. That's the conditional VE and GAN. So I think I want to stop here because all the others are about the technical details about the Weierstrass GAN. I don't plan to talk about it, but I want to say the latest architecture of a GAN is based on the Weierstrass GAN. So basically, you don't need to train a logit. When you train a discriminator, you don't need to use a logit and a logistic unit, output unit. You just need to remove that kind of logistic unit, and then and then that kind of like a distance corresponds to the Weierstrass distance y, and then just under why it is important, because the Weierstrass, if you use a logistic output unit, you don't have you have the gradient vanishing problem. But when you use the Weierstrass distance, you don't have the gradient vanishing, especially your generate data doesn't overlap with your input data. And then if you use a Weierstrass distance, you always get a gradient. And then and then the training algorithm is the same, but you need to use a weight clipping. What's weight clipping does, and then just clip the weight into a range. Make sure weight is always say -5 to 5, so something like that. And I will not talk about the details of Weierstrass GAN. You can study by yourself. So this is the latest GAN architecture. You can see all these kind of images are fake images. You can see we can generate so good, like a high resolution images, even videos like this. Hopefully, this is my current work. So that's it. I want to stop here. So any questions so far about the GAN or even Weierstrass GAN you want to? So the technical detail is that just don't use the logistic unit, because when you use a discriminator, traditionally people just train a logistic unit, output 1 or 0. But now you just a linear feature, okay? Just a linear feature and then sum it, and that's it. Make sure the feature representations separated from each other. That's it. For scalar output. And no logistic. Don't go through that kind of logistic output unit. For the scalar score. So that's it. Thank you so much. Any questions about the conditional GAN, conditional VE, or like GAN architecture? So the training, if you want to train it, just my suggestion about training the VE and GAN is that always start from some kind of like open source package that already show good results. Don't code it by yourself if you don't have enough time, because there are lots of like technical details we need to pay attention. Even I do it. I will like start from a well-established like a GAN framework, for example, style GAN, or for training images, or for conditional GAN, you probably start from like a projection GAN. So I don't plan to talk about it, but I think the advice is that always start from a well-established open source package in PyTorch, and then so you can modify by yourself. Thanks so much. Yep.
I have another question
Yep.
about I think you mentioned examples of when to use the autoencoders. Can you mention again, like?
Oh, well, you mean a deterministic or variational autoencoder?
Both. I don't understand. Like
the autoencoder, you see, the autoencoder is just like just for learning good representations, right? You see, this is good. For example, you don't have let's go back to the architecture of the autoencoder here, right? So you see, in this lecture we covered the variational autoencoder and the GAN, right? They are both unsupervised learning algorithm. So the GAN, you can see, it is used for like for generate some data, right? That is similar to your data point. You may wonder, why do we need to generate some data, right? And then I will tell you that one way of is that you, as we talk about, you can do domain adaptation, right? You can use this kind of adversarial idea for domain adaptation. You can use it for generating more training data examples to augment your current data, right? So that is, you want to get more data to train something, you can use the GAN architecture. And the variational autoencoder is even better. First of all, it can be used for generating data. Second, you can get the low dimensional representation of your, where is it? Of your data, right? You see, right? You have a lot of data. You want to know, and then for example, I want to do some classification, right? And then if you don't have enough data, and then you can probably you don't have billions of data points, you don't have billions of label data points, and then you can probably train a variational autoencoder to embed this kind of data to low dimensional space for visualization and train a classifier in this kind of low dimensional embedding space. This is the first usage you can use a variational autoencoder. The second is that you can even sorry, what do I say? You can even use it for denoising, right? For example, your data has some kind of noise, and then you can use a variational autoencoder and then to just like embed it and then try to reconstruct it to denoise the original inputs. So does it make sense?
Yes, that is super helpful. Thank you.
Thanks. Any other questions? I saw the chat. What is it? Thank you. Okay, then no questions, and thanks so much. And it's my pleasure to give these 3 lectures. And if you're interested in biomedical research or other machine learning research at ANC Labs America, please email me. You can see we always publish the top tier conferences in the NeurIPS, ICML, and ICLR, and then we even get the awards from these kind of conferences. I would say the machine learning department is very strong, even compared to Google brand and Facebook, because you see the Yan Kang or Yusha Benju, they both are one stayed in our group. And then the PyTorch, I want to mention that ANC Labs America holds the copyright of PyTorch because Torch was developed starting in our lab. Okay, thank you. Have a great day. Bye.
Thanks a lot, Renqi. Take care.